morning everyone. My name is Alisha Kalyani. I am from Government Degree College, Hyderabad. We are doing Jignasa study project in chemistry under the supervision of Zohaman and Nasrkan.
I am Nano from GDC second year.
Myself Subi, I am studying in GDC second year.
I am Zibat from GDC final year.
I am Milani Begum from GDC first year.
And our topic name is Nanomine AI powered prediction of nanoparticle antibacterial efficiency. As we know that antibacterial resistance is a major problem in our modern medicine. Nanoparticle offers a promising alternative and due to their unique properties, interacting with the bacteria in many ways. Their unique physiochemical and different properties, their large surface of area ratio volume, and they have tunable composition. They can be used as these properties allow nanoparticles to engage with the bacterial cells differently than traditional antibacterials. However, evaluating this antibacterial capacity is the challenging way to the factors of the particle size, the surface charge, temperature, and also chemical nature of this. These traditional experiments are time-consuming and costly. Nanoparticles use computational approaches to have this nanoparticle performance, providing the insights to hidden of the different things as information and harnessing AI power information, which help us accelerate the different researches, reduce the experimental expenses, and also help us with guidance of towards the structure and things that can affect the nanomaterials. This work aims to bridge the gap between the lab research and the real-world application, helping the combat of the antibacterial resistance. Further reconfigured by Yusra.
The problem statement is antibacterial resistance is a threat to global health and it depends on size, morphology, surface chemistry, and scientists has to do a lot of efforts. So we are doing a project on AI-based technology, and the objectives are of project Nanomine AI powered prediction of nanoparticle antibacterial efficiency that aims to identify key nanoparticle properties that affect antibacterial activity. Here we are understanding the power of it. Build an AI-based framework to predict efficiency. Here we input the size and shape to predict it. Minimize dependence on the length lab experiments. Guide the design of a nanoparticle. Promote faster, cost-efficient solutions. Further will be continued by Subia.
Here is introduction to nanotechnology. Size range of nanoparticles is about 1 to 100 nanometers. 1 nanometer is equal to 10 to the power of minus 9 meters. Surface area increases drastically at nanoscale, high reactivity due to quantum effects. For example, if particle size decreases from 100 to 10 nanometers, surface area increases about 10 times more. Types of antibacterial nanoparticles. First one is silver nanoparticle, size between 5 to 15 nanometers, strong antibacterial activity, shows strong antibacterial activity. Second one is zinc oxide nanoparticles, band gap of 3.37 electron volts, generate reactive oxygen species. Finally, titanium dioxide nanoparticles, band gap of 3.2 electron volts, UV activated antibacterial action. Bacterial targets. There are two types of bacteria. Escherichia coli give gram negative with a thin cell wall of 2 to 7 nanometers. Second one is Staphylococcus aureus give gram positive with a thick cell wall of 20 to 80 nanometers. In this image, we can see these two types of bacteria with a different cell walls thickness. Further will be continued by Zero.
Here are the mechanism. The very first mechanism is cell membrane damage. Nanoparticle size which is less than 20 nanometers penetrate easily into the cell membrane. Surface charge interaction zeta potential 30 microvolts. Disrupts the phospholipid barrier. As a result, leakage of cytoplasmic content occurs. The second mechanism, reactive oxygen species. ROS, which is commonly known as ROS. The common ROS are superoxide hydroxyl radicals. Example, zinc oxide nanoparticle produce ROS under light, which is lambda 365 nanometers. Here the third mechanism involves in metal ion exchange. Silver nanoparticle releases Ag plus ion. Typical concentration is about 10 to 50 microgram per milliliter inhibit bacterial growth. MLC value 5 to 20 micrograms per milliliter. Here the different kind of machine learning modules. The very first is linear regression, random forest, and neural network. Among these, the neural network is highly accurate. Here the two different kinds of graphs here, the concentration versus bacteria and the bacterial inhibition and machine learning model accuracy. Here the nanomine kind of nanomine workflow diagram. Here input parameters which shows the size, charge and concentration. If we input in AI models, it gives a efficient output. Further will be continued by Ilan.
Here is application and conclusion. In application, medical implants to reduce infection, and then warm dressing to wound heal faster. In water purification to remove bacteria from water. In food packaging to store food for long time, and in hospital coating to prevent the spread of bacteria. In conclusion, we can say that the smaller nanoparticle, the size is from 10 to 20 nanometers, shows 85 to 95% efficiency, and artificial intelligence reduces cost up to 40% and time up to 60%. Nanomine integrates chemistry plus artificial intelligence for a smart antibacterial design. Future scopes are real-time artificial intelligence integrated laboratory systems